Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Ladies and gentlemen, welcome to my webinar about pure hydrogen generation. In this video, we're gonna talk about the principles and the basics of generating pure hydrogen gas by water electrolysis. It's a very important technology nowadays, and it is a step towards the hydrogen society. The development countries now are trying to get their share in this society for the development of renewable energy, and to decrease the consumption of the fuel, the fossil fuel. Okay, so let's get started. So here, pure hydrogen production by water electrolysis using PV panels. We're going to talk about this is the main content, but we have to take a look on the principles. So this is the way to a hydrogen society, the green hydrogen. Like this, using the solar panels, then you can use the hydrogen cars. No CO2, no soot, no any no any hazardous. Okay, no any hazardous. Like the Japanese say, this is our dream to enter the hydrogen society. Watashi tachi no yume. Here are the contents. Here are the general principles. Alkaline electrolyzers, proton exchange membrane electrolyzers, solid oxide electrolyzers, reversible fuel cells, HHO technology, HHO separator cell, the design of the project, references. We're gonna talk about our design, my own design. I designed it, I think, 3 years ago, and it was a great project, but you know that it has to you have to get the funding to apply this in the real life. So the general principles: the electrolysis of water is the decomposition of water H2O into oxygen and hydrogen gases due to an electric current being passed through the water. This technique can be used to make hydrogen fuel, to hydrogen gas, and breathable oxygen. But we have to add some additive to the water. An electrical power source is connected to two electrodes or two plates, typically made from some inert metal, such as platinum, stainless steel, or iridium, which are placed in the water. Hydrogen will appear at the cathode, the negatively charged electrode. Why? Because H will be H positive, where electrons enter the water, and the oxygen will appear at the anode, the positively charged electrode, like this. So this is the very simple technique here, H2O, and we have cathode and anode, and a battery 9 or to 12 volts, and we have here positive and negative, and we have H2O, and it is not recommended at all to be a tap water, and you have to use distilled water to avoid any salts or any problems. So assuming ideal Faradic efficiency, the amount of hydrogen generated is twice the amount of oxygen, and both are proportional to the total electrical charge conducted by the solution. However, in many cells, competing sides reactions dominate, resulting in different products and less than ideal Faradic efficiency. Faraday efficiency, also called Faradic efficiency, Faradic yield, or Coulombic efficiency or current efficiency. Describes the efficiency with which charge electrons are transferred in a system facilitating an electrochemical reaction. The sources of Faradic losses are experienced by both electrolytic and galvanic cells when electrons or ions participate in unwanted side reactions. These losses appear as heat and or chemical byproducts. That's why if we check out or measure the temperature of the cell, we will find the temperature increases with time. So an example can be found in the oxidation of water at the positive electrode in electrolysis. Some electrons are diverted into the production of hydrogen peroxide. The fraction of electrons so diverted represent a Faradic loss and vary between different apparatus. During water electrolysis, the desired products, hydrogen and oxygen, could combine to form water. And here is the secret. So this could realistically happen in the presence of catalytic materials such as platinum or palladium or NaOH, KOH, commonly used as electrodes, but here is so this could realistically happen in the presence of catalytic material such as platinum or palladium, commonly used as electrodes. Electrolysis of pure water requires excess energy in the form of overpotential 1.23 volts theoretically to overcome various activation barriers. Without excess energy, the electrolysis of pure water occurs very slowly or not at all. So this is in part due to the limited self-ionization of water. So we have to get excess energy using a high voltage electrical source like 9 or 12 volts. The efficiency of electrolysis is increased through the addition of an electrolyte, and here we go, such as salt, acid, or base, and the use of electrocatalysts. So the more the electrocatalysts are in the solution, the more productivity it will be. Okay, so we have electrolyte NaOH or KOH are commonly used. One important use of electrolysis to produce hydrogen. The reaction that occurs is 2H2O, here aqueous to 2H2 as gas plus O2 as gas. That's why the volume of the hydrogen is twice the volume of the oxygen. And here are the anode positive, and here are the equations, and you can find out these equations in the literature. And here are the anode, and here are the cathode. So this has been suggested as a way of shifting society towards using hydrogen as an energy carrier for powering electric motors and internal combustion engines without any toxicity. Electrolysis of water can be achieved in a simple hands-on project where electricity from a battery is passed through a cup of water. In practice, a salt water solution or other electrolyte will need to be used, otherwise no result will be observed. So the recommended separator of hydrogen and oxygen is Nephron, because it prevents the formation of side reactions, because it allows only water and proton to pass, but it is very expensive. So we have here a deal to produce the hydroxy gas. It contains hydrogen and oxygen as a mixture. It's not water, but it is a hydrogen plus oxygen. You can use it as a fuel, okay, or a flammable gas. But if you wanna get only pure hydrogen, you have to use the separator or the membrane, like Nafion. This is from the website Fuel Cells, and here Nafion 117, and we have here the price per sheet, and this is 3 years ago. Okay, so the price $32, and I think this is good. Not, but this is the highest. This is the highly cost membrane or the parts. This is the high cost part. Here is the anode and cathode, and here is the electrolyte and electrolyzer reactions. We see here H2O enters the cell, and here H positive, H positive, H positive, and here is the oxygen. And so we have to, so we get pure hydrogen if there is a membrane. And here the electron, and here the cell voltage to H2O enters from here, and here we have O2 out and H2 out if there is a membrane. If there is no any membranes, we will get H2 plus O2 as a mixture, but two gases. So for each mole of H2O consumed, 1 mole of H2 is generated and 2 moles of electrons are passed through the external circuit. To convert electron flow, moles of electrons per second, to electrical current, coulombs per second or amps, one would use Faraday's constant, coulombs per mole of electrons. The rate of hydrogen production is directly related to the current as follows. Okay, so that's why the more current in the cell is, the more productivity of hydrogen. To be in electrolysis mode, the voltage must be greater than voltage corresponding to zero current. This voltage is called the open circuit voltage, and theoretically it's equal to 1.23 volt. The hydrogen reaction rate is directly proportional to the current, since for each hydrogen molecule that reacts, 2 electrons are formed. For electrolysis, operating voltages EOP must be greater than EOCV. Hydrogen is produced with an external power source. This is indicated by negative current values. So over the entire range of current densities, there is a linear fall in voltage as the current density increases. Assuming fast kinetics, this voltage drop is caused by a resistance to H positive flow across the electrolyte membrane. In this case, the operating voltage can be described as EOP equal EOCV minus I multiplied by R multiplied by A, where I is the current density, R is the resistance, and A is the cross-sectional area of the electrolyzer. In physics and electrical engineering, this effect is referred to as Ohm's law. While an electrolyzer uses an electrochemical device for separation of water into hydrogen and oxygen, it draws many parallels to typical membrane separation processes across a dense membrane. Our primary interest is the rate of H2 production. However, H positive is the species transported across the membrane, and so the flux across the membrane is written with respect to H positive. Like this, we have here, for every 1 mole of H2 produced, 2 moles of E minus and 2 moles of H positive are produced at the end. The flux equations for an electrolyzer and the separation with a dense membrane are compared below. We have here Ni and L, and this is the CIO and CIL. You can check out all these from the research papers and the theoretical literature. We find many equations that cover the simple principles. And we have here the nomenclature. Okay, and here are the concentrations at the membrane interfaces, CIO and CIL, and the current density, and so on. and here the L of the thickness of the membrane. So we have here, if we think their relation, I think that the thickness of the membrane has to be small to increase the rate of productivity and to decrease the resistance. So the only difference between the flux equations for the electrolyzer and membrane separation is that the electrolyzer takes into account electrical ions. For the electrolyzer, voltage directly corresponds to the concentration of oxygen at each membrane interface via the Nernst equation. The concentration of oxygen is typically expressed as a partial pressure of oxygen, PO2, like this. And here we have the equations. You can write it using any equation solver like engineering equation solver software is, and then you can study the what if questions. So you can change any number here and get the results, and you can decide if this is suitable for your project or not. We always have to determine the area of the membrane to purchase it. And here the area of the cell, 91 square meter, or whatever the unit is, based on the basic equations. We have here our overall system design from a research paper. I think the first step in the system design was to determine the desired characteristics of the electrolyzer to produce at least 0.5 kilograms of hydrogen at a pressure sufficient for fueling. Fuel cells, I think, Valence LLC, NC Milford, ST could make a high pressure electrolyzer capable of reaching an output pressure of 6500 psi. Very high, as a very high pressure without any compressor. Such electrolysis builds up the pressure in a contained system. This is from a research paper, and we have here this electrolyzer would contain 48 cells, and if the cells were put into banks of 24, the cell voltage when operated at a nominal current of 130 amperes or amps will produce 2.8 kilogram of hydrogen per day. Wow! So thus the system would consume approximately 6.5 kilowatts to make 2.8 kilogram of hydrogen in 24 hours of operation. And here is the kilowatt hour. To make 0.5 kilogram of H2 would require approximately 28 kilowatt hour of electrical energy. At a pressure of 44.8 megapascals, 6.4 kilogram of compressed hydrogen could be stored in a 231 tanks for dispensing to fuel cells. So whatever the numbers are, we have here a grid for the voltage. Here the AC rectifier 6.5 kilowatt at nominal 50 V direct current output. Okay, and here 4 solar arrays, and here DC converter, and here we have water input, water purification, and here the distilled water, I think, and here the system, and here the control electronics and battery system, battery charger, and here we get the H2 at this psi, and then we get this H2 as a fuel. Okay, and it's the source of the fuel to the fuel cells. Okay, so this is used in the hydrogen cars. We get the H2 and we use the fuel cells to produce electricity. Okay, the fuel cells is like the turbine. We use fossil fuels for the turbines, But here for the fuel cells we use H2, and then the fuel cells produces electricity for the cars. Here is from the reference we have a research paper. I think it was published in the research the Science Direct, okay, in the paper of the Journal of Hydrogen. We have here the details of the operating conditions of the system, of their system. This is not our system. So we have, you can get this paper and check out the details. Okay, and here is the system. This image where was published in their paper, and here is the high pressurized system for generating for the H2 generation, and so on. Okay, and here are the some of the details. Okay, now we have to talk about the solid oxide electrolyzer cell. A solid oxide electrolyzer cell, SOEC, is a solid oxide fuel cell that runs in a regenerative mode to achieve the electrolysis of water, and which uses a solid oxide or ceramic electrolyte to produce oxygen and hydrogen gas. The production of pure hydrogen is compelling because it is a clean fuel that can be stored easily, thus making it a potential alternative to batteries which have a low storage capacity and create high amounts of waste materials. Electrolysis is currently the most promising method of hydrogen production from water due to high efficiency of conversion and relatively low required energy input when compared to thermochemical and photocatalytic methods. And here our system, and you can check out the details from the internet or the research papers. So the operation, the general function of the electrolyze cell is to split water in the form of steam into pure H2 and O2. Steam is fed into the porous cathode. When a voltage is applied, the steam moves to the cathode electrolyte interface and is reduced to form pure H2 and oxygen ions. The hydrogen gas then diffuses back up through the cathode and is collected at its surface as hydrogen fuel, while the oxygen ions are conducted through the dense electrolyte. So the electrolyte, the most common electrolyte, again similar to solid oxide fuel cells, is a dense ionic conductor consisting of ZrO2 doped with 8 mole percentage Y2O3, also known as YSZ. Zirconia dioxide is used because of its high strength, high melting temperature, approximately 2700 Celsius, and excellent corrosion resistance. So the fuel electrode of the cathode, the most common fuel electrode material is an Ni doped YSZ. However, under high steam partial pressures and low hydrogen partial pressures at the NiYSZ interface cause oxidation of the nickel and leads to irreversible degradation. The oxygen, or the anode here, the oxygen electrode, lanthanum, strontium, magnet, LSM, manganate, is the most common oxygen electrode material. LSM offers high performance under electrolysis conditions due to the generation of oxygen vacancies under anodic polarization that aid oxygen diffusion. So the electrolyte must be dense enough that the steam and hydrogen gas cannot diffuse through and lead to recombination of H2 and O2. At the electrolyte anode interface, the oxygen ions are oxidized to form pure oxygen gas, which is collected at the surface of the anode. Now I have to talk about another technology, proton exchange membrane, polymer electrolyte membrane. PEM electrolysis is the electrolysis of water in a cell equipped with a solid polymer electrolyte. And here the electrolyte is not liquid like NaOH or KOH, but here is solid. That's responsible for the conduction of protons, separation of product gases, and the electrical insulation of the electrodes. PEM electrolyzer was introduced to overcome the issues of partial load, low current density, and low pressure operation currently plaguing the alkaline electrolyzer. Electrolysis is an important new technology for the production of hydrogen to be used as an energy carrier with fast dynamic response times, large operational ranges, high efficiencies, and very high gas purities, 99.99999%. Also, here is the efficiency or the benefit from using PEM electrolyzer. The PEM electrolysis is a promising alternative for energy storage, like we said. And here the PEM electrolysis on cathode and anode, and these same equations are here. And here the information about the diaphragm and the cell density, the cell area, and the cell current, and so on. And here we go, this is the benefit using solar energy, no need to use any other electrical source from the grid or the AC current. Why? Because we want to hear a DC current supply, so the best thing to use is the solar cell. So just using the solar cell will produce the required electricity to run this great project and get the H2 and the O2. Every gas is in the tank, but we must use the membrane. And here at PEM water electrolysis, many research papers talked about this. You can check it out on the Science Direct or ResearchGate or any other website. Okay, and here is the current collector and the catalyst coated membrane, and it's a very high technology. And here is the spreader plate. It's not easy to be carried out at home. No, it requires high funding actually, because it is a very high accuracy, and it requires many things to be done. And here are the advantages of disadvantages of alkaline and PEM electrolysis. So the advantages: well-established technology, and here high current densities, high voltage, efficiency, and have good partial load range, rapid system response, compact system design, high gas purity, and here is dynamic operation. But the disadvantages, so here the advantages: well established technology, non-noble catalysts, long-term stability, relative low cost, and so on. You can see the advantages of the three systems, and here are the disadvantages of the three systems. Okay, so Faraday losses and crossover, like we said, the Faraday losses describe the efficiency losses that are related to the current that is supplied without leading to hydrogen at the cathodic gas outlet. The produced hydrogen and oxygen can permeate across the membrane, referred to as crossover. Mixtures of both gases at the electrodes result. The cathode oxygen can be catalytically reacted with hydrogen on the platinum surface of the cathodic catalyst. At the anode, hydrogen and oxygen do not react at the iridium oxide catalyst. Thus, safety hazards due to explosive anodic mixtures hydrogen in oxygen can result. That's why we have to carry out these experiments or these designs. We have to be careful due to these hazards. The supplied energy for the hydrogen production is lost. So when hydrogen is lost due to the reaction with oxygen at the cathode and permeation from the cathode across the membrane to the anode corresponds. Okay. So this system is not easy, and hence the ratio of the amount of lost and produced hydrogen determines the Faraday losses. At pressurized operation of the electrolyzer, the crossover and the correlated Faraday efficiency losses increase. So I have here the electricity and hydrogen and biogas, natural gas, and here are we see the hydrogen society or the plan of the developed countries. It's very important to check out your plans and to see what's going on and how to avoid using the fossil fuels and this. So we have here H Generators. It's a company uses a special technique of producing hydrogen. You can check it out from on the internet. And here their productivity in milliliters per minute and the prices. So as you see, it's very you will pay a high cost. It's a high cost energy or a high cost fuel, but it is very clean compared to the fossil fuels. That's why we have to find out many ways to decrease the cost and increase the productivity of hydrogen by using many techniques, and we're going to talk about in this video or the next video. So that's why we have to find another low-cost techniques and the ways that you can carry out or use at the faculty or any small-scale laboratory, such as the HHO hydrogen generators or the hydroxy generators. So, gentlemen, if you wanna watch a video about the HHO wet cell, please, I will highly recommend watching this video. It's a very good video. So now we can watch the HHO dry cell. Okay. Here is the pure hydrogen. The previous technique was a mixture, but here O2 and H2. Why? Because they use the membrane. Here two hoses, and here pure hydrogen bubbler and the oxygen are important to for the safety cautions. The chemical is collected from the bubbler. The water here is to prevent any spark. There's nothing flammable, so let's take a look on the H2. Here the power supply, we can use solar. So let's take a look on the oxygen. It is not flammable gas. Here's the oxygen extraction. Here is a cigarette, and only oxygen increases the flammability, but it is not a flammable gas. This is the combustion. Only oxygen. Yes. O2. Now, yeah, the pure O2. Now here are the O2, but no flames. No flames. Yes. Yeah, made in France. Well, have a nice time. So it's a very simple technology, but H2 is a very flammable gas, explosive. Thanks, Hydro, and you can. This is Hydropolit. You can visit their website. Thanks, well done, great job. Thank you, merci. Now, gentlemen, why is the HHO dry cell a better design? When the edges of the plates of a HHO generator are submerged in the water catalyst bath, a great deal of the electrical current passes through the edges of the plates. This current is largely wasted in terms of HHO production. When the edges are outside of the bath, like the dry cell, as with the HHO dry cell, all of the current is forced to travel directly to the faces of the plates. Therefore, all the current supplied to the HHO generator is utilized efficiently, making HHO gas. The electrolyte bath attacks and will eventually destroy the electrical connections if they are submerged. With the HHO dry cell design, they are outside the water catalyst solution, which is stored in a separate reservoir and recirculated by the HHO dry cell, providing the cell is designed correctly. This helps in producing more HHO gas and less heat steam. The plates of their HHO dry cell are made of 316L 18-gauge stainless steel. You will see many cell designers with 20 gauge or less. We prefer to use thicker material to ensure you will get a lifetime of usage from your system without wear out. Of course, this is the statement of the company. 316L has been found to have the best priorities resistance to attack from the process of electrolysis. However, mounting hardware, wire, and cable are very difficult to find in 316L grid and are unnecessary, not to mention very costly to use. So wet HHO cell disadvantages. The wet cell design has the electrode plates, anode equal positive supply and cathode negative supply, fully submerged in the electrolyte solution till the oxygen which gathers around the positive electrode anode will start reacting with the metal surface, creating oxidization. Oxidization. This will eventually erode the plate and needs to be replaced. That's why I think they replace it every 6 months. Another disadvantage is excess heat generation in wet type HHO cell, as the heat generated from the electrolysis process has no escape route. Eventually, this will start heating the electrolyte solution the longer it's run. Because of this excessive heat temperature, more steam is produced and mixes with the hydroxy gas. But the dry HHO cell design, the name of HHO dry cell, mainly came from the most significant difference from the wet cell design, and that's because the outer edges of the plates and the connections are sealed from the wet area. Each plate comes with a gasket to seal the outer edges from getting wet. The name might be slightly misleading because this type of dry cell still uses the same principle of water electrolysis to generate the HHO gas, only with greater efficiency because there is no extra heat energy being produced. The electrolyte is stored in an external expansion tank, often called the bubbler, similar to a radiator expansion tank, and the electrolyte enters the HHO cell by gravity. Once the hydroxy gas produced through the electrolysis process, which is lighter than the electrolyte, it has no other option but to rise back to the top. And here is the beauty or the intelligence of this system. This continues until the HHO gas reaches the bubbler and rises above the electrolyte storage. The bubbler tank has a dedicated outlet on top, so the gas is forced through it. The pressure needed is automatically created by the bubbles created during the electrolysis process. Therefore, no additional pump is needed. So the advantages, the good news is that less maintenance is required as long as there is no excessive heat on the HHO generator, which will shorten the life cycle of the seals. It's best to install it in a cool place, ideally where there is less engine heat being transmitted to the generator unit. This amperage per cycle to produce the required amount of HHO gas. The design is more robust and durable by nature. Less maintenance for the same amount of working hours. More efficient, no excessive heat buildup, like we said, being produced as wasted energy. More space efficient, the flat design allows for more plates to be added for only minimal thickness. Less oxidation because the limited electrolyte volume per cycle and the electrical connections are totally isolated to the external body of the generator. The same amount of HHO gas or more can be produced with less amperage. Cleaner electrolyte solution because of less oxidation on the anode plates compared to the wet cell. The dry HHO generator acts as a self-pumping action to the electrolyte solution. So the dry HHO cell disadvantages. There are not many disadvantages apart from when maintenance comes into play. Okay, the dry HHO cell unit has to be totally taken apart for the seals to be replaced. This process takes more time compared to the wet design. So the membrane materials, polyester, monofilament mesh works with sodium hydroxide NaOH. And the nylon monofilament mesh works with potassium hydroxide KOH. We got this information from the websites. So silk screen mesh T165. The uncoated rib stop nylon, 300 cross thread count per inch is recommended or higher. And here is the gasket. Holes match up with barb fitting holes in the plates. And the membrane, if you wanna separate or get a pure H2, you must use the membrane. If you don't wanna get pure H2, you wanna HHO Hydroxy as a mixture to be used in the cars as a direct fuel. No need for storage. You don't have to use the membrane. And I know people who use the HHO dry cell without any membranes, and they installed it in their cars, and it was very good. No soot, no CO2, no CO. So membrane here is centered over the gasket. Membrane is smaller than gasket. Gasket has two seal membrane, and you know that holes must be cut in membrane. Holes must match up with holes in plates. Holes in membrane match up with barb filling holes in the plates and gasket. Rotate second gasket like this and place on top of membrane. Holes match up. So it will be necessary to make a jig with pegs that fit the holes. Use it to build the gasket membrane and membrane as a unit. The membrane needs to be glued to the gasket as you go. Separation gasket and membrane assembled. Each consists of two gaskets with membrane sandwiched and glued between them. These were boiled for 5 minutes after the glue dried. The heat tightens the membrane by shrinking it slightly. This process makes the gasket easy to handle. It also makes the cell easier to assemble. And here we go, here the HHO cell, the end plate, and the gasket plate, and here the end plate, gasket. The same procedure, but there is membrane. So this is the difference between the HHO cell that's used in cars and here the separation cell that's used to store the H2 as a pure gas. And also can get pure O2, and this is used in the hospitals as an oxygen in the oxygen tanks. So here positive, negative, positive, this is the orientation, and the gasket hole creates a channel. The slot in the gasket lets the gas into the channel. Multiple cell stacks require reversing the position of the gasket hole slots for each stack. In other words, one stack will have cut out on the left, the other stack on the right. And this is necessary in order to keep the gases separated, collecting in the right channel. So let's check out this great video.
สวัสดีค่ะ My name is Ubalat Pai. I'm going to show you how to make the hydrogen cells. First of all, these are the assembly kit, and all of them are the parts. These are the end plates. We have left and right. The inside surfaces have chamfered holes. All the threads are prepared with 2 nuts and a washer. All the stainless steel plates are scored with the sandpaper. We have bronze gasket and a special gasket. we have a special membrane that have been cut by a laser. The insulated tube are put onto the jig. First, we put on the blind gasket and put the glue, a special glue, on the blind gasket, and then we put on the first active stainless steel plate. We put a special glue on the active stainless steel plate and then put the special gasket on the top. We now put the special membrane on the top and apply with the special glue. The glue set quickly in a few seconds, and we shrink the membranes with the hot air gun. We add the first neutral plate. We now do more 3 times, so we have 4 neutral plates. We now have added 4 neutral plates and 4 membranes. They are nice and tight. Notice the slot. We now added titanium plate. We now added the titanium plate. Now the stack is now ready for the last stainless steel active plate. And we add the next blind gasket. We add the blast connection bolt. We add the end plate with the blast bolt and the chamfered hole get over with the plastic tube. Now ready for the bolts. Use the drill at low speed, but do not push.
And now, ladies and gentlemen, thank you very much. This is the fantastic project. Thank you, ma'am. Merci, danke, and благодаря. Great job, nice project. This is the dry cell, HHO, using the technology of the membrane. So hopefully this information will help advance dry cell technology or the advanced. A few experiments are using nylon or use nylon monofilament mesh to divide water chambers into two areas, one for hydrogen and one for oxygen. To get an idea of how this is done, watch the videos below. This is from the website, okay, and like the videos we watched. Notice that they are using two gaskets between each set of plates. The nylon mesh is inserted between the two gaskets, red line in the picture above. We're gonna see these pictures now. Mesh inserted between two gaskets, okay. The mesh keeps the hydrogen on one side and the oxygen on the other side. There are special slots, like we watched in the video, in the gaskets for channeling the gases to separate gas output ports. Instead of HHO coming out of one port, hydrogen and oxygen have their own ports, and here is the technology of the separation. Watch the videos, okay? Okay, that was used by the early. And here we see, notice that the gas outlet port in the left, there is a slot cut in the gasket, so the gases on the side of nylon membrane can escape through the hole. The other side of the hole looks like the hole on the far right. The gasket seals the hole so the gases cannot enter on the other side. Mix. The membrane separates the gases. The slots in the gasket pass or block the gases, keeping them separated. By alternating the slots, gases can be collected and kept separated. Okay. So I have tested. They have tested this method of separation, and it does separate the gases quite well. It also allows the water to refill to the chambers. It easily passes through the membrane. So the mesh forms a thin wall that allows the water to pass through it, but not the bubbles. The H and O ions pass through the water, cross the membrane, and form the gas on the electrode plate. They are attracted to positive or negative. The hydrogen stays on the negative side on the membrane wall, and the oxygen stays on the positive side. The mesh is a dividing wall. It forms or separates two chambers. The gases rise to the top of their respective side of the chambers and collect at the top. They escape through the hole in the electrode plate. So it's very important to make holes in the mesh that match up with the holes in the plates. Cut out holes for the water and for the gas. If you do not, back pressure will be created, and that could cause the gases to mix. The gases take the path of least resistance. So the gasket materials are high temperature neoprene rubber or EPDM rubber or silicone. It's also important to note that pack pressure can cause the gases to mix. That means we need to make it as easy as possible for the gases to escape through the holes and also through their respective bubblers. Pressures should be the same in both bubblers. That means the water levels need to be the same, so it may be necessary to equalize the water levels via a hose between them. Thank you, ladies and gentlemen, very much for your patience in this webinar. The next video, we're gonna talk about the design or the detailed design of the dry HHO cell that I created 3 years ago using Autodesk Inventor. I'm gonna talk about the stainless steel or the plates, the membrane, the design of them, and the holes and the threads and many things, and the design of the bubblers, and we're gonna see or watch many videos. Thank you very much. I wish this helps you, and I think it's a great step on the way to the hydrogen society or the green renewable energy. Thank you very much. Wassalamu alaikum warahmatullahi ta'ala wa barakatuh. Thank you very much, and you can see here the literature or the research paper. Here is by Alexandria Engineering journal. This is available in those are, I think there are Egyptians, Alexandria University in Egypt, on the effect of hydroxy HHO gas addition on gasoline engine performance and emissions. You can skim through this, and here the bubbler and the HHO and the same system, and is the dry cell, and this their own design, and you can see many good things here and the conclusion, and you can check out many research papers on hydrogen generation, Science Direct. Okay, you can check out sustainable hydrogen production and HHO cells. Okay, effect of hydroxy, International Journal of Hydrogen Energy. You can check out all these websites and get these papers. Thank you very much, and assalamu alaikum wa rahmatullahi ta'ala wa barakatuh.